Welcome back! In the previous video, we presented a framework in which we will be able to write text and binary files with our microcontroller by implementing the parts marked with to do. However, to do this, you will need to know a few more useful functions. With this video, we want to help you write the program.
It's worth pausing the video now and reviewing the framework program structure in detail if you haven't already done that. The functions in the FatFs library often expect structures as parameters that are defined in the library. We will cover these now.
Let's go in calling order, and let's look at the FatFsTestMount function first.
This function mounts the FAT32 file system on the SD card, meaning we ask the FatFs library to read the data describing the FAT32 file system from the SD card. This operation should only be performed once when the microcontroller is booted. It is not necessary to perform it before each file operation. You can use the FatFs library's fmount function to mount the FAT32 file system. It has three parameters. The first is a pointer to a FatFs structure that represents the file system for the FatFs library and can be used to refer to the file system later. In the framework software, we have already created a FatFs structure called FileSysObj. Let's use it. The second parameter is the path where the file system is mounted, represented as a string. This has to be a variable called sdPath, since the generated code when initializing the FatFs directory also uses this. The third parameter can be 0 or 1. 0 tells the FatFs directory not to read FAT32 descriptors yet, only when we start the first file operation. 1 means that calling the fmount function will also result in FAT32 descriptors being read. Now we will use the value 1, so we will immediately get feedback from the FatFs library if something is wrong with the FAT32 file system of the SD card. The return value of the function is of type fResult, which can be a variety of error messages. If the function has run without error, the return value is frOK, otherwise it is some kind of error code.
Our next function is the FatFsTestReadString. If the text.txt file does not already exist on the SD card, it will create it, insert the natural numbers from 0 to 255, separated by \n, new line characters, and finally close the file. Do not leave a file open, as this can lead to all sorts of problems. You can write to the SD card only per block and only per cluster when using the FAT32 file system. That is, if less than one block or one cluster of data is written to a file, the FatFs library will not immediately write the data, but will store it in a temporary storage in the RAM. Closing the file will result in the data actually being written to the card. So if the file is not closed and the power is removed, both the file system and the contents of the file will be corrupted.
To open files, we can use the fopen function. This is absolutely necessary to perform read and/or write operations on a file. Its first parameter is a pointer to the file structure, which is then our reference to the file. In the framework software, we can use the file string structure for this purpose for a text file. The second parameter is a string that indicates the path to the file. For the text file, this should be text.txt. The third parameter is a number representing the different ways to open the file. It is actually an 8-bit parameter, each bit carrying a specific piece of information. For easy code readability, we can use the binary OR connection of the FatFs library preprocessor definitions to produce the appropriate parameter. The possible options can be found in the FatFs ff.h header file and are shown on the screen now. In case of FA-read, we want to read from the file. FA-write is a write mode which can be combined with FA-read, so in that way we can read and write to the file. If FA-open_existing is used, the fopen function returns an error if the file does not exist. With FA-create_new, a new file can be created, but fopen returns with an error if the file already exists. In contrast, FACreate always is used to create a new file anyway, even if there is already one on the specified path. In this case, the existing file is overwritten. FAOpen always opens the file. If the file doesn't exist, it creates an empty one. FAOpenAppend is similar to FAOpenAlways, except that the read or write starts from the end of the file.
So, to write the file text.txt, we need to use the combination FAWrite and FACreateAlways, and thus fopen will return frExist to indicate if the file already exists. The return value of fopen is also of type fResult, so frOK if everything was OK, and some error code if not.
The fprintf function is basically the same as printf. The only difference is that it writes to a file, meaning that you write ASCII characters in the text mode. Its first parameter is a pointer to the fill structure, which tells which file to write to. This pointer was used to call fopen before. In the case of the FatFsTestReadString function, here we have to use the file string structure. The other parameters, if used, work in a similar way to printf. So, if you want to print an integer followed by a new line character, you have to use the %d\n string and the number you want to write in place of %d as the third parameter. The return value of fprintf is a number representing the number of characters printed, or negative if an error occurred.
The fclose function is used to close the file and at the same time write all data to the SD card. It has only one pointer type parameter pointing to the fill structure, which tells it which file to close. Its return value is of type fResult, with the same meaning as described for the other FatFs functions.
In summary, it's worth noting the following sequence of operations, since in practice this pattern should always be followed. First, we open the file, then read from or write to it, and after it we close it.
Our next function to be implemented is the FatFsTestReadBinary. If the binary.bin file does not already exist on the SD card, it will create it, write the natural numbers 0 to 255 in binary, and then close the file. The first step here is also to open the file with the fopen function. In this case, the file binary structure and the FAWrite, FACreateNew open modes are used. You cannot write to the file in binary using fprintf, because this function writes ASCII characters to the file. For example, for the number 123, it writes 3 bytes, hexa 49, 50, and 51, since these are ASCII codes corresponding to the characters 1, 2, and 3.
To write a binary file, you can use the fwrite function. It is used to write the contents of an array of bytes to a file. Its first parameter is a pointer to the fill structure, which tells it which file to write to. This pointer was used to call fopen before. Now we need to use the file binary structure. Its second parameter is a pointer of type void star, pointing to the memory address of the first byte to be written. Its third parameter is an integer, which tells us how many bytes we want to read from the memory area pointed to by the second parameter. The fourth parameter is a pointer to a variable of type integer. Basically, this is the variable that the function will write the number of bytes it has successfully read. The return value of the function is of type fResult and should be interpreted in the usual way. After the write is complete, you can then use the fclose function to close the file.
After this comes our text file check function, which opens the file text.txt, reads the contents of the file and compares it with the previously written data to see if the write operation was successful, and finally closes the file. To open the file, we can use the fopen function with the file string structure and faread mode.
The fgets function can also come in handy, which reads an ASCII string from a file one line at a time until it finds a \n character. Its first parameter is an array of characters into which it reads the next line from the file. Here, the 10-element array strread is already created. Let's use it. The second parameter is the length of the array in bytes. The third parameter is a pointer to the fill structure, which tells you which file to read from. The return value is a pointer, which is null if the end of the file is reached or if some error occurred during the read. If all went well, it returns its first parameter.
Among the standard C functions is ATOI, which produces a number from a string representing a number. It has one parameter, which is the string itself, and the return value is the number. For example, calling ATOI with the string 1452 will return 1452 as a result. We will need this now, because we want to check the numbers written to the text file, which are already in the file as strings, not numbers, and we need to convert them back somehow in order to compare them with the value written. After the read is complete, we can then use the fclose function to close the file.
Our last task is to verify the binary file. The FatFsTestReadBinary function opens the binary.bin file, reads the contents of the file, compares it with the previously written data to see if the write was successful, and then closes the file. The file can be opened again using the fopen function with the file binary structure and FA-read mode. To read a binary file, we can use the fread function. Its first parameter is a pointer to the file structure, which tells it which file to read from. Its second parameter is a memory address where the data should be written to, which is typically an array. The third parameter is the number of bytes to read. The fourth parameter is a pointer to an integer variable, the value of which will be set by the function to the number of bytes to be read. Its return value is of type fResult, which is interpreted in the usual way. After the read is complete, the fclose function can then be used to close the file.
The first step is to format the SD card to FAT32 using your computer. It's important to note that formatting will lose all the data on the SD card, so if you have important data on it, save it to another medium first. You can use an external or built-in card reader to connect the SD card to your computer. To format a drive on Windows 10, you have to right-click on the drive you want to format and then left-click on the Format menu. In the window that opens, select the FAT32 file system and click on the Start button. The other settings can be left at their default values. After formatting, remove your memory card and insert it into the SD card reader on your embedded system.
Then you can download the software onto the development board. We have already done so. If my colleague takes it and plugs the USB cable into the laptop in the slot of the memory card reader, the software should run. Visibly, the two LEDs were lit, which means that both the text and binary file were successfully written. If LED 1 and LED 2 are not lit, then use breakpoints as described in the previous example code to find the source of the error. If you fail to find out the cause of the error, you can find the finished software on our website called Lecture 23 FatFS Example, from which you can cheat. Keep in mind that each new run will rewrite the files, thus reducing the lifetime of the card.
It might be interesting to remove the SD card from the circuit and use your computer to re-download the files.
Of course, it only works if you don't forget to do it.
Well, it's important to remove the power first and then the card. And maybe turning on the camera would also help.
Oh no. Well, sometimes we forget things.
We will find that the computer can now see the two files, and we can view their contents. If all went well, we can open text.txt with any text editor and see that it contains numbers and the new lines. To view the binary contents of the binary.bin file, we need a special software. Now we will use the HXD application for this purpose. We will see that the file does indeed contain the numbers between 0 and 255, represented by bytes.
Rename the binary.bin file to binary.txt and double-click it. You will see that first you see strange characters, then special characters, numbers, letters, and finally strange characters again. What's the reason for this? We didn't change the data itself, just the name of the file, and yet the content has changed. Of course not. Your computer's operating system uses the file extension, the part after the last dot in the file name, to decide which program to open to interpret the file's contents. Actually, all files are binary files, a series of bytes. They become something like a text file by interpreting the bytes as ASCII characters rather than as music, movies, or as other things. So, we still see the same numeric values, just in ASCII representation.
I think we have all the necessary information to implement a real-time data collecting app with the help of our Nucleo board. In the next video, we will make a device that can sense brightness. Join us there too. Bye.
Bye.